Okay.
Yeah.
Okay,
Oh,
let's do
you're
the number
muted.
one.
Oh,
Yeah,
there you go.
okay. Let's go. Let's do the number one. What effect did the amplitude have on the period of the pendulum? Well, that's fairly easy because the period didn't change with amplitude at all. So
Right.
no, doesn't have any effect.
That's what you're supposed to notice, right? Perfect.
Yes. Number two, it is reasonable that it will take longer to travel a greater distance. What might explain the observation that this did not happen? That one, I don't know what to answer.
Okay, so they're trying to do this. Remember the question before that. You just said that more amplitude didn't change the period.
Yes.
So what they're trying to get you to think about is, okay, if you have the pendulum and you make a bigger amplitude, it's got to travel further.
Yes.
And you're supposed to say yes, but it travels faster. So it takes the same amount of time.
Okay.
And the two balance each other. So more amplitude is a further distance, but it's also faster. And that's the idea of that one.
So the answer would be that. Exactly. I didn't follow. Say it wrong again. Say it
So
again.
you'll want to say, so the bigger amplitude, which is more distance, is also faster.
Oh, I see. Yes.
So it takes the same amount of time.
Okay, perfect. Then the next question is, what effect did weight on the period of the pendulum have? Actually, none. Didn't have any effect because the period did not change with the mass.
Right. Right.
That's right. Then since weight is the force that causes the pendulum to swing, it seems reasonable that a greater weight would accelerate faster. Why did this not happen?
Okay. So again, more weight, as you just said, didn't change the period.
Yes.
And your first thought might be more weight is more force.
Ah, correct. Yes.
But it is also more mass or more inertia.
Oh yeah, more resistance to change.
So you end up with the same acceleration.
Oh yeah, you're right because so
Yeah, in fact,
the resistance.
right. In fact, the pendulum isn't any different than the way back at the beginning of this course when we said drop a pebble and drop an elephant.
Okay.
The elephant weighs more, and your first reaction might go, wow, that's more force. But the elephant also has more mass. And so all the objects fall at 9.8. It's a ratio of F over M. Mm-hmm.
All right, great. Okay. The other is, what effect did length have on the period of the pendulum? Well, the length, it did have some. So as length increases, the period increases, but it is not proportional.
Correct. It's not proportional. Okay, yeah, perfect. It's not proportional. Yeah, that's perfect.
Yeah, because usually the curve goes a little bit funny. That's why the curve goes curve, correct?
Right,
The first graph.
Exactly.
So number 6 is, if the length was proportional to period, how long would the period of 15 centimeters and 50 centimeters pendulum compare?
Okay, so when something is proportional, that means they go up by the same factor. So 15 up to 150 means you're multiplying by 10.
So that
okay. So if you look at your period, and you can't really look at it yet because you don't have that last answer. But if you look at the time for the 15 and you multiply it by 10, you do not get the period of the 150.
All right. Okay, so I have to multiply that to 15 and I'll see what happens, correct?
Yeah.
Yeah,
Yeah.
by 10. I mean, yeah.
So wait, read that question again so I can answer it a little better.
So if length was proportional to period, how would the period of a 15 centimeters and 150 centimeters pendulum compare?
Yeah, so the answer would be, it would be 10 times greater.
Okay.
Yeah.
Okay, that sounds great. So
10
then
times
next,
greater.
yeah.
And then, of course, it's not 10 times greater, you know, because you
Yeah.
already said it's not proportional, but they just said that it's a hypothetical question, if it was. Yeah.
Yes. So next one is, what was, I said, was this that you observed, was this what you observed for your pendulum? No, that's not what I observed.
Yeah, right.
Correct?
That's
Because it's not
correct.
proportional, yes.
Not proportional, right.
Yes, and then next one, number 7 is, what seems reasonable for the relationship between period and length? Explain your answer.
What is reasonable?
For the relationship between period and length.
Yeah.
I mean,
that's not an easy one to answer, but I'll tell you what it is. It's the square root of the length.
the square root of what? Sorry?
Of the length.
Oh.
So your length increased by a factor of 10, right?
Yes.
If you take the square root of 10, you get about 3.1.
Okay.
And again, I'm sorry you don't have their last piece of data, but if you look at the period for the 15 and you multiply it by the square root of 10, which is 3.1, you will get that period for the 151.
All right.
Yeah.
Okay, so that's good. Number 8 is using log graph paper. What was the predicted period of a 300 centimeters pendulum? Okay, that one, I don't know exactly, but when I did the I don't know what exactly you want, but when I did the graph, it was 3.4.
Perfect. Yeah, I saw that on your graph.
That was the predicted, so okay. Yeah. So then that's the answer for that one.
That is the
So then the next one is, what was the measured period? But that's the same question.
So no, well, one of them, what's the predicted? That's what you got off your graph. And the other one is, what did you actually measure? And that's the part where you said the video cut out. I need to look that up for you.
Oh, I see. So that's the other answer. Okay, so that's it. Okay.
Yeah. And I will get those to you, but yeah, that's the one. And it is about 3.4. So your predicted and what I actually measured is, you know, they're right on cue. So you're good.
Okay. So I think that's pretty much it. So maybe see you Friday, because now I think these chapters are kind of not easy, but they're more fair. I don't know what happened, but I'm going faster. So I already began working on chapters today. I finished my other chapters, so well, with your help too, because Anyway, that's pretty much it. I think actually, by the way, chapter 15, I think it was the rope. That was chapter 15 that we were the rope. That chapter is very interesting, but I fell asleep 3 times reading the book. I don't know why. It was so difficult for me to do that. Okay.
Yeah, those standing wave problems are tough ones. You asked one by email about that fundamental one, and that's 2 of the 3 you asked are kind of hard to kind of do.
But let me tell you this. The funny thing is that the last question that I asked you, it is in the book.
Oh, it is? Okay.
It is, but it is in a different wording that you did.
Okay.
So that's what happened, is that the wording that they use it confused me. So, but I didn't know. I read the book again. I said, I kind of read this, but then I went back and it's there, but they answered in a different confusing wording. So like I said, the way you teach is really, really amazing. So I actually, it's in my head. Now I just know all these things very well.
Good.
Okay.
Very
Okay,
good.
I'll let you be with my other classmates, and thank you, Professor.
All right.
I hope you keep being strong and being distracted, and see you Friday, okay?
Okay. Bye.
Bye. Bye.
Hi, Professor.
Hey, Parker. How you
I'm in
doing?
your 123 class, if you didn't know.
Oh, okay.
I had a question on the homework, the 39 homework,
Yeah.
number 6.
Let's see. Chapter 39, number 6. Okay. Let me do a couple things here. Maybe the first is to look up my camera again. Needed to take it down after the break. Yeah. Bummer. There we go. Should write down number 6. Okay. Good. And then let's me jump over here and do a screen share. And get the Bluetooth started. All right, and while that's trying to connect, let me find the homework number 6. Looks like it says an astronaut, huh?
Yeah.
All right. All right, good. Let's work through this one. It says, so an astronaut is traveling in a space vehicle moving at half the speed of light relative to the Earth. The astronaut measures her pulse rate to be 75 beats per minute. Signals generated by the astronaut's pulse are then radioed to Earth when the vehicle is moving in a direction perpendicular to the line that connects the vehicle with the observer. What does that mean? Oh, an astronaut's pulse is radioed to the Earth in a vehicle that is moving in a direction that is perpendicular to the line connecting the vehicle to the observer of the Earth. Okay, so A, what pulse rate does the Earth-based observer measure? Okay, so the big step in this is that amazingly, I always find it amazing that if you have the following condition that the speed of light is the same for all observers, then time cannot be the same for all observers. So I hope that came out through the video link well, because that's a big surprise, because Newton and everybody up until Einstein had always just said, well, if somebody's moving or not, it doesn't really matter. The time that they observe is the same. Now, if you do that, then the speed of light can't be the same. But starting at early on, about the 1800s, that's when the experiments started showing that the speed of light is the same for all observers. And that didn't really make sense to people, but they kind of just accepted it. But it was Einstein who went a step further and said, well, if the speed of light is the same for each observer, then the time is not. And that was the revolution. And there was many other consequences because of this whole thing that time is affected. Anyways, so we have this equation that the time difference between one observer and another observer are related by this factor of gamma, okay? Where this factor right here, this sub p, that is what we call the proper time. And so now, just to kind of clarify, here's the challenge that the world faces now that time depends upon the observer, is then when we say delta t, we also have to say, well, who's doing the observing? These are all different. So we don't want to make it sound like one is right and one is wrong, but we do want some kind of commonality that we can address this. And so the commonality is to say that if you are measuring, say, in this case, your pulse, and the clock that is measuring the pulse is not moving relative to you, we will call that then the proper time. So that if somebody else moving, so I'll put a little spaceship here, and they have a clock, their clock would be moving relative to the event, your pulse, and therefore they're going to measure a different time, and so we call that a non-proper time. All right, so what we have, and I like to make a little diagram here, is we have what we would call this proper time, where there's no motion, and then there's an infinite different amount of motion. You could have something moving at 10% the speed of light, so they would measure a non-proper time, or something that could be moving at 20% the speed of light, so there's another non-proper time, or 30. You get the idea. So there's an infinite number of non-proper times, but there's only one proper time. And so knowing which one we have and which one we're looking for is a big step. And then that helps us move along. Okay, so let's read this carefully. We go back to the astronaut. It says an astronaut is traveling in a space vehicle moving at some speed, half the speed of light relative to the Earth. Okay, now this is the key part. The astronaut measures her rate. So she is measuring her own rate.
Right, so that's a proper time because it's not
Right,
moving.
so the clock she is using has no motion between her, and I think that's why they used pulse. So it would be very clear that there's no motion between that clock and her. Okay, so I'm going to say this then is a proper time. Now we could do the whole time of, well, let me do a rate. Okay, so let's do this. Let's see, what is her pulse? So according to her, she has 75 beats in 1 minute. Let me write it here. So 75 beats per 60 seconds. How about I do that?
Yeah.
Now let me look at the reciprocal of that, because that's a time. So if I look at 60 seconds for 75 beats.
So that was part of my question, is why can't we just use the beats per second? Why does it have to be seconds per beats?
Well, it's a time. If you use beats per second, you're doing a rate.
Okay.
And you're doing the reciprocal.
Okay.
Now, we could, take our original formula up here and take 1 over, but I think that might be more confusing. So I could rewrite this in terms of rates.
Okay.
And it would work out just as well. But that's not my original reaction. My initial reaction is to figure out what the time is.
Okay.
Okay, so my first response is to say that I have a time of 0.8 seconds. That is the time between beats. So knowing that, I can then come over and say, okay, what would somebody on Earth observe? What time between beats? So that's where the gamma factor comes in.
And just gamma is unitless, right?
You're correct. Gamma is
Okay.
just a number.
Yep.
And it's based upon how fast the other observer is going.
Right.
That's why there's an infinite number of different possible observations. Let's see, the speed of the Earth would be half the speed of light. So I'm going to put in half the speed of light for v divided by the speed of light. So that's the gamma factor. And then this is the proper time. So the gamma factor would be this 1 minus 0.5 squared. Then it would be the square root of that. Then it would be the reciprocal of that. All right. So the gamma factor is 1.155.
Yep.
And so that phrase we like to say is, moving clocks run slow. So this, the person on Earth is going to say, as they look out maybe in their telescope and they look at the astronaut, they're going to say, wait a minute, your clock's running slow by this factor. So you got 75, beats, but it was running slow. Times 0.8. So this Earth observer is going to say that there is actually 0.924 seconds in one beat. So to take the reciprocal to get a rate, meaning one beat in 0.924 seconds.
Mm-hmm. And then 60 seconds.
And then multiply by 60 seconds in a minute is going to give us the number of beats in a minute. So taking the reciprocal and then multiplying by 60, pretty close to 65 beats per minute is what the person on the Earth would say.
Mm-hmm.
They'd be saying, look, the only reason you got 75 is you actually measured more than a minute.
Right.
Your clock is running slow.
Okay. Yeah, I think the confusion in this problem just started, pretty well understood it, except for why you had to use seconds instead of the rate.
Yeah. So, and I would say you don't have to, but our formula is set up with time, not with rate. So we'd have to readjust our formula. So I think it's better just to take the rate and make it a time and use what they've given us.
Yeah. All right. That was it.
So what number was this? 6?
That was 6.
Oh, good. Oh, wait, there's a B?
I think the B is it's pretty much just using a different velocity.
Oh, okay.
Yeah.
Sounds like you're good with that.
Mm-hmm.
Okay.
All right. Thank you, Professor.
You bet. All right. Maybe I'll switch over here. I saw one come in here by email. I believe it was another, where'd it go? 121. Yes, here. So let's see. Let me write down a time. 103. Yeah, and so this is the, how do they call this? Oh, the kind of looks like a wheel or a wheelchair here going up a curb here. So pushing a wheel over a curb. All right. Well, good. Let's talk about this one. Again, more torque stuff. And a chance for you 121 people to do some of this harder stuff. And for me to say that, remember, we can calculate torque around any axis. So if you've seen any of my videos this week, and I think this is the fourth one related to something around a torque calculation, you'll know that these torque calculations can be done around any axis. At least that's what I want to keep emphasizing here. So let me just read the problem here. It says a wheel with a mass of 1.16 kilograms, radius of 0.295 meters, is initially at rest. It touches the curb that has a height of 0.154 meters. A horizontal force is applied to the axis at the center of the wheel. The minimum force required to lift the wheel off the ground is F sub minimum. And then they give us a very important hint that I want to talk about again, I think for the third time, is that you can pick any axis you want and pick the one that makes it the easiest. And so it says, hint, choose an origin such that you don't have to calculate the unknown force F of the curve. And we are to solve for F minimum. All right, so let me start with these 4 steps again. And step 1 is getting a good physical picture of what's going on. Step 2 is the free body diagram. Step 3 is writing out the equations. And step 4 is solving it. So starting again with step 1, good physical picture. It looks like, if you think about a wheel just kind of getting up to the edge of the curb, maybe barely touching it or not touching it at all, and nobody pushing it forward, there would be this weight pushing down, mg. And then at the contact, and my drawing wasn't quite so good, the center of mass here going down should be right at the contact point of the wheel. So this would be the normal force from the ground pushing up. And that's all you would have at this point. However, once you start pushing the wheel forward, okay, so there's a force F, you now make contact with that curb. And so now the curb pushes back. Now, as I said in a couple of other videos and want to repeat here, when a solid object like a curb is pushing back, you don't really know what direction it is. Now, in the author's diagram, he just has a force of the curb kind of pointing up this way. I'm going to do that in green. Force of the curb. And there's nothing wrong with that. But I want to emphasize that a good way to handle these with unknown is to call them an X component and a Y component. A good symbol I like to use is the R. I call this the R for reaction force, because you push the wheel into the curb and now the curb pushes back. Okay, so these are our reaction forces. So whether you want to look at this as one force at an angle, some unknown angle, so those are your 2 unknowns, the magnitude of the force and the angle, or look at it as 2 unknowns that you have an X component and a Y component, it's kind of the same thing. But please don't look at this as 3 forces. This is really just 2 unknowns. Either the magnitude and direction are unknown, or the X and Y components are unknown. Okay. Now, when we go to calculate torques, so sum of the torques equals I alpha. I have been saying in the other videos, and want to emphasize it now, that if you pick your pivot point to be the place where an unknown force is touching it, you will get 0 torque. Because remember, the way you calculate torque, and I'll put kind of the 2 important formulas here, is this RF sine phi, or the perpendicular distance. And if I do this distance here, this R means the distance from the pivot to where the force is acting. And if we're talking about the force from the curb, where the curb is the pivot, the distance then is 0. And so we would get 0 torque from the curb. And so when you go to write out all the torques, you don't have to worry about or even think about the curb one. That's the beauty of it. So that's what I want to emphasize is a good, wise choice of where do you calculate the torque. Okay, so in this case, the wise choice, I think, is right here at the curb. Now, like I said, the author here of this problem gives us that helpful hint. But at some point, I think the author is going to stop giving those, and you got to kind of figure that out on your own. So I want you to know why that is such a good point. And so now that I think I've done that in 4 videos, you're hopefully getting that and sinking in. Okay. Now, there's also something else here, because I think one of the things that might make this a little bit harder is we're trying to actually lift the wheel up. And you may argue, well, wait a minute. Lifting the wheel up is moving. And so this is not really an equilibrium problem. And I would say, well, it kind of is still an equilibrium problem. Because if you're talking about just the minimum amount of force to lift you really are talking about barely turning it. And so any force greater than that force, when you set the acceleration equal to 0, would be the minimum. So the minimum would be any force greater than or equal to just enough to make this an acceleration of 0 when, and here's a big piece, when you're just lifting it off the ground so that the normal force also goes to 0. Did you catch that? I'm going to say that again because this problem isn't quite like all the other ones. This one truly is not an equilibrium. But that doesn't mean we can't say, okay, what's the minimum? So even though this is not an equilibrium, we can still argue that the minimum force is sort of like an equilibrium problem where it's just enough force that it lifts it off the ground and the normal force now goes to 0, but not quite enough yet to make it rotate. So we apply the angular acceleration to 0 and the normal force equal to 0. Now, let me do a better free body diagram here, okay? Because now that we have a good physical picture of what's going on, and what I mean by that then is right here is going to be the pivot point I will calculate. There will be a force, which we're looking for, pushing the wheel forward. There will be the weight of the wheel, but there will no longer be a normal force. And although there will be a force from the curb, and so I will put it in my free body diagram, I'm not going to pay any attention to it because I'm going to calculate the torques and set it equal to 0. And the torque I get from the curb is unnecessary. And so what I have is a torque from gravity and a torque from this minimum force. So remembering that torque is calculated this way, I will put the torque from the force plus the torque from gravity is 0. Now, I'll come back to this diagram, but I'm going to need another page here. So the torque from the force using this, the perpendicular distance times the force, would be this piece right here. Let me just call that a Y for a moment. That torque would then be Y times force minimum. Whoops, that's not a Y. Y times force minimum. And is that a positive or a negative torque? Well, again, if this is the pivot, you push this way, that tends to make it rotate in a clockwise direction. Traditionally, clockwise is a negative. So let me just stick to the tradition. So my torque from this force is a negative torque. There's the perpendicular distance and there's the force. Likewise, the torque from gravity would be the perpendicular distance. So let me just kind of draw. That would be the perpendicular distance from the line of force to the pivot. Let me just call that an X for a moment. And so that would be X times its force, which is mg, and that would be a positive torque. Positive because if you think about this as the pivot and gravity is pulling it down, that would make this wheel rotate in a counterclockwise direction. Now, of course, in reality, it can't actually move counterclockwise because then it would hit the ground and there would be a normal force. So I understand that it doesn't really move that way. But without a normal force and without this force pushing it, that's the way it would want to go. And so that's how I calculate its torque as a positive, and then has to come out to be 0. So after a little bit of adjustments of my symbols, the minimum force then would be this xmg over this y. All right, so now we should probably start talking about then what is the x and what is the y. Maybe the easiest one I think to see is the y here, because they told me the height of the curb. The height of the curb was 0.154. And, the radius of the wheel right here is 0.295. So y would be the difference between the radius and the height of the curb. This is the part that's left over from the curb on up to the top. Okay, so this would be 0.295 minus 0.154. So there's my y. My g is 9.8. The mass is the 1.16. Now, the x might take a little more work. I'll use the Pythagorean theorem. You saw that in a couple of the other videos, but particularly the one with the can. If I draw across here, then this x squared, y squared would be r squared. So maybe I'll just write that on the side here. The x squared plus the y squared is then equal to the radius squared. What symbol should I use? I'll use a capital R. I don't see anything in there. Okay. Now, I haven't actually calculated the y, but maybe this would be a good time to do that. So 0.295 minus 1.54 gives me 0.141. So that's the y. And that can be useful here because remember, then x squared plus, and then there's the y squared, 0.141 squared. And then here's the r squared, 0.295 squared. And that will allow me to find this x. So 0.295 squared minus 0.141 squared, and then taking the square roots is 0.259. That seemed a little big. Let me just test that. Squared plus, well, that's kind of small. 141, and when you square it, even more so. And square root. Do I get that? Yeah, I do. Okay. All right. So there's my x. So let me put my x over here, 0.259. And now we can actually finish the calculation and get a number. So 0.295. Let me come up here a little bit higher. See things. Pull my hand out of the way in case I was blocking anything earlier. You can see it now. Okay, so there's the 0.295. There's the 1.16. And there's the 9.8. Now divide it by the 0.414. And I get a 23.8. Ooh. And, oh, my bad. I had done that calculation and I used the answer. I didn't want the 295. Let me try that again. I wanted the 0.25. No, but I saw that. Okay. So 259 times 1.16 times 9.8 divided by 0.141. Okay, and then about a 20.9. And so hopefully that helped somewhat. Good. Go back over to the